Good afternoon, ladies and gentlemen. I welcome you to this presentation or tutorial about LTE, but I think the key subject is not to explain LTE to you in all details, because here we would need much more than 1 hour or 1.5 hours. I think when we would go into all the details of LTE, we would need at least 2 to 3 days. So, but the key question here is the following. What can we do, or what do the broadband industry, what is the broadband industry? It's the Verizons, the AT&Ts, and all those guys. What can they do with this new LTE standard? Can they use it for broadcast? And what are their intentions? So that's what we will discuss, I would say, within the next 1 hour, 1 hour and 50 minutes about. So, on one hand side, we have the broadcast industry. That means it's the industry which makes classical TV. On one hand side. On the other side, we have the broadband industry. As already mentioned, all those providers for the service of our smartphones, the Verizons, AT&Ts, and so on. And both of them, they are fighting for one single good. And this good is what? Frequency. Frequency, they need. Of course, the broadcast industry, they have a lot of frequencies. And the broadband industry, they want to have those frequencies. And here we see already, this is the fight. So, a short outline. We will discuss a little bit how it works, the growth of the mobile data capacity. That means what are the reasons that more and more data capacity is needed by the broadband industry. I will give you a short introduction to the technology behind LTE. We will talk about the structure of LTE and the modulation scheme. And then we will come to the most interesting point, MBMS, Multimedia Broadcast Multicast Service, a feature which is part of LTE, and this feature allows us to use LTE also for conventional broadcast. And last but not least, we will make a comparison between the broadcast and the broadband industry, and then we will come to the summary. So let's first have a look to the increasing demand to data capacity. Broadband is an emerging technology. Everybody of us uses here a smartphone, and nobody really want to miss it. And that our smartphones work, we need bandwidth. That's clear. And meanwhile, our smartphones are so intelligent that they can even be used for media services. We can stream TV, we can stream audio, IPTV, IP audio. I think this is common to all modern smartphones today. And here we have to distinguish between 2 kinds of broadband technologies. First, when we talk about fixed broadband, what is it? This is the broadband which is delivered to our home via cable, fiber optics, or even TV coax cable. And here we have the huge amount of data capacity available, even so much that we can use this fixed broadband technology for linear TV streaming. New word, linear TV streaming, what is it? Under linear TV, we understand the conventional TV or the conventional audio as we know it. It means TV content is transmitted and we can just receive it. We have no influence, we cannot stop it, we cannot pause it, or we cannot forward it. That's what we have, that's what we understand under linear TV. So that means in some areas, especially where we have fiber optic, broadband is meanwhile so strong that this technology can be used also for linear TV transmission. And here, this is also a clear point that the broadband industry, the fixed broadband, already endangers the conventional broadcast industry. But this is another story. So, when we talk about linear TV, we also have non-linear TV. What is it? Non-linear transmission is IPTV or IP radio. That means I have a peer-to-peer connection between a server, and I can stop the video, I can forward it, I can start it again. That's what we understand under non-linear video transmission. So, this is related to fixed broadband, and here we do not see any capacity problems. But the situation is totally different when we talk about wireless connectivity. As already mentioned, everybody uses a smartphone and nobody wants to miss it. And here we are facing a strong bottleneck. Frequencies, bandwidth for terrestrial transmission. When we look to the data capacity projected, and here a good choice is the annual Cisco report, and I have taken here some data from the annual Cisco report 2012. So the annual Cisco report says that the data rate for wireless broadband applications increased 8-fold over the last 4 years. And it will increase again 8 times in the next 4 years. So that means by 2016, and 2016 is not far away from now, we will have a monthly data transmission capacity of 10.8 exabyte per month. 10.8 exabyte, the exabyte is 10 power to 18. That means 1 billion times 1 gigabyte. This is a huge number. And when we just have a look to the number here in the US, you see it here, the dark red. Here this report predicts that the data capacity will increase to 1.7 exabyte per month. And the key point is that about 68, or let's say 70% of this data is just related to video transmission. Just video transmission. And when we compare it with other countries, for example Europe, Asia, here the situation is nearly the same. It's nearly identical. How was this possible? The mobile 2G technology, just like GSM, GPRS, or Edge, had a theoretical data capacity of just 10 kilobit per second. So, but this is the past. Then we had the 3G technology with WCDMA and HSDPA. Here we had theoretical data capacity of 14 megabit per second. In reality, we know it's just 7.2 megabit per second. This is a technology most of us use today when we make an internet connection with our smartphone. End of 2008, the 3GPP. What is the 3GPP? This is the third generation partnership program. Started to define the long-term evolution of UMTS. It's also called as 4G technology. And the name is long-term evolution. What are the partners of those 3GPP. I think here we have all major telecommunication player in the world. For example, the ARIP in Japan, ETSI in Europe, the ATIS here in the US, in Korea, in Japan, and the CCSA in China. That means all major players are involved here. So here we see on this slide a short summary of all those technology. We will talk about here about this blue one, this 4G technology, and we see already the data capacity just for download is in the range up to 100 megabit per second. That's a huge number. And here we also see the applications here. That means we have stationary applications, we have mobile applications and fast mobile applications in fast driving cars or fast driving trains. And here we see that of course the data rate goes down, but it's still high compared with the 3G technology or the 2G technology we have before. So that's the technology we will talk about, LTE. And of course there are already activities for further enhancement, the data rate up to 1 gigabit per second. So when this technology was defined, starting in 2008, what had been the parameters? First, the data rate. The data rate should be high, quite high compared with the 3G technology. So that means it was defined that the peak download data rate should be in the range of 100 megabit per second. And for upload, 50 megabit per second should be possible. This was the first requirement. The second requirement was related to the latency. So the latency, that means the delay from, let's say, of a packet, for example, from the base station to the user equipment should be less than 5 milliseconds. That's a huge improvement compared with the technology, the 3G technology we have so far. Later on we will see why this is a big improvement. And furthermore, the so-called C-plane latency. What is it? The C-plane latency just describes the wake-up time for the system. And this should be less than 100 milliseconds. The bandwidth should be quite flexible. There should be bandwidths possible in the range of 1.4, 3, 5, 10, 15, and 20 megahertz. So that means the bandwidth should be adjustable to the environment in the different cameras. And, quite important, multimedia broadcast, multicast services, MBMS, should be possible. That's the reason we even can talk about to use this technology for TV broadcast. MBMS is not totally new to LTE. It was already specified in release 7. That means for UTMS. But for UTMS, this broadcast technology could not really be used. And last but not least, the requirement was related to mobility. So this standard should provide the maximum data capacity, let's say 100 megabit per second for download, up to speed to 15 kilometers per hour. But the system should also work in case of really high speed, for example, high speed trains, up to a speed of 350 kilometers per hour. But in this case, of course, with lower data rate. So this had been all the requirements. And to fulfill all those requirements, new transmission technologies were needed. And the choice was a technology we already know from digital television. Not digital television here in the US, ATSC, but from digital television we know it in Europe and in Japan, in China. This is OFDM, orthogonal frequency multiplex. This technology, OFDM, orthogonal frequency division multiplex, XS. As far as this XS is concerned, I will come to this a little bit later. So this is used for the downlink, and for the uplink, another technology is used. It's single carrier frequency division multiplex. I will come to this later why we use another technology for the uplink and we do not use normal ordinary OFDM as we have it in the downlink. Spectrum allocation. LTE defines two different operation modes. First, frequency division duplex, FDD, and time division duplex, TDD. To explain to you, we see it on this frequency map. For example, here we have FTD. That means we have different frequency bands for upload and download. For example, here from 1920 to 1980 megahertz, that means 60 megahertz, we use for the upload, and again, other 60 megahertz band from 2.11 gigahertz to 2.17 gigahertz we use for the download. In the same way, here, so that means we have paired frequencies for upload and download, and for the TDD operation mode, time division multiplex, we use the same frequency band and we use upload and download once after the other. So, this is broadband, but on the other hand, this is broadband. On the other hand, we have the classical linear broadcast services. While here we have these nonlinear services they can provide, and here we have the classical linear services. And those two parties, they fight. As already mentioned, they fight for one single good, and this good are the frequencies. Actual available frequencies, of course, they depend from country to country. Yeah? And here I have just shown the frequencies available in Europe and in the US. So that means those frequencies have already been drastically reduced. That means already several frequency bands have been transferred from the broadcast industry to the broadband industry. This is the frequency range from 792 to 862. Upper red part, which have already been transferred. This is the so-called digital dividend. This frequency range is used or should be used to deliver high-speed internet to the countryside where we don't have the right cable infrastructure and so on. And the second red area, this is the frequency range from 694 to 792. This frequency range was co-allocated in the last year World Radio Conference. Co-allocated means that from 2015 onwards, this frequency band can be used for broadcast, but it can also be used for broadband. So that means we have a further reduction of the TV broadcast frequencies. And here below we see the situation in the US. Similar, that means the remaining frequencies for broadcast are about 300 megahertz. Here below, we see the frequencies allocated to the broadband industry. So that means here in dark red, we see the FDD frequency range. We see always two actually use for UMTS. So, that's the situation today. But the broadband industry, yeah, those guys, they're requesting for, or decrying for more frequencies. In some papers, we can read that up to 2020, another 1.3 gigahertz bandwidth is needed for broadband, and at least 500 megahertz in the next 5 years. And they also request that at least 100 megahertz should come from the broadcast industry. Further 100 megahertz. And what are the arguments of the broadband industry? They argue with the increasing demand, especially for video transmission. We have seen video transmission is 70% of the complete mobile data. Furthermore, the increasing demand for machine-to-machine communication we will face in the future. And the further argument is that the broadband industry, with the new technology, LTE, they can even also handle linear television and radio transmission. So, they raise the question, at least some of them, is terrestrial broadcast even still needed? Because we can do it also by our own. So, give us more frequencies, maybe next year a little bit, and then more and more until we have all the frequencies. Not. So, what they do not tell us, of course, there is a huge business. I was told, I cannot really say whether this figure is right, that a television bandwidth of 8 megahertz, in Europe we have 8 megahertz, here in the US it's just 6 megahertz, has a value for the broadband industry for a country like Germany of 1 billion euro. That means 1.3 billion US dollar per year. Germany is much smaller than the US, so that means for the US, maybe this would have a value of $4 billion per year, just for one 8 megahertz TV channel. So there's a big business behind. And furthermore, we should also not forget that those frequencies are sold by the government to the broadband industry. And as more frequencies are available, as cheaper the prices. So that means there are, of course, strong business interests behind. So let's come a little bit to technology we use in LTE. As already mentioned, we use as transmission technology OFDM, orthogonal frequency division multiplex access. For those who are not familiar with OFDM, I will just summarize it. Let us assume we have here a channel of 5 megahertz bandwidth, and within this channel we have a certain number of frequencies, each spacing with 15 kilohertz. And despite the fact that those frequencies are overlapping, they do not influence each other due to the orthogonality. Yeah? When you look right, that means, for example, where this carrier has its maximum, the others have a 0%. That means we have here orthogonal frequencies. In this case, for example, 300. And each of these frequencies is modulated either with QPSK, by means 2 bits per symbol, or is modulated with 16 QAM, 4 bit per symbol, or 64 QAM, 6 bit per symbol. So that means that those frequencies are transmitted during this symbol time, and then we switch to the next symbol.